We are now going to look at a very fundamental problem, and it will also serve as an application of the Chebyshevs inequality. The problem is that of finding the median element in an unsorted array. So the input is an array S of n distinct integers. I mean, they don't really need to be distinct, but for simplicity, we're going to assume that they're distinct. And of course, we're going to assume that the array is arbitrarily permuted, because if it is sorted, then finding the median is trivial. So the output, the required output, is the median element m. And those of you who have taken a basic algorithms course might recall that there is an O of n time algorithm to find the median, and that runs in deterministic O of n time and is always correct. However, the advantage of this algorithm is that it's simple to implement and also serves to illustrate Chebyshev's inequality. So from that point of view, we're going to study this problem. And the key idea is the following. So we have an input array S. Let's view this array in its sorted form. I'll have to emphasize here that the input is arbitrarily permuted. When we're talking about the sorted view, we're purely talking about the array from analysis point of view. So there's no sorting that's actually happening. Okay. So in this sorted view, the middle element, of course, is the median. And the idea behind this algorithm is to find two elements, D and U, on either side of M. And hopefully these two elements are close to M. So what do we mean by that? Let's define C to be the set of all elements in the array S that lie between D and U. Okay, and we want that set C to be small. In particular, we want that to be little o of n over log n. And this will mean that if you sort C, you only require little o of n time. Okay, and if you're able to find such elements D and U such that these properties hold, so D is on D and U are on either side of M, and the set C that we've defined here is small. These are the requirements. Now, suppose we're able to find these elements, then we can find the median, and here's how that will work. Let's say we're able to find the D and U as we require. Then it's easy for us to compute C. You just have to scan the entire set S, the array S, and find all the elements that are that have values between D and U. And so that will provide us with the set C. In that process, you can also find the order of D, the position of D in the sorted view of S. Think about that. That's fairly easy to find. And so then what we do is we sort the set C. And now think about it. It's given the order or the position of the item D in the sorted view of S, and the fact that you have sorted C, it should be easy now to find the median. So take a moment, pause, and make sure you know how the median can be computed under this context. Now that you've had a chance to think a little bit and make sure you understand the high-level idea, let's actually look at the details. So here's how the formal algorithm goes. This algorithm is taken straight out of Mitzenmacher and Ufal. Okay, so the notations are as we have defined. The set S is the set of elements that we want to order, from which we want to find the median. And here's how the algorithm goes. First, we need to figure out how to uh, compute D and U. And how do we do that? We achieve that by sampling. So we have to pick a set R, where each element in this R is chosen uniformly at random. So that's R for us. Each element is in R is chosen uniformly at random and independent of each other from the set S. Okay, and how many such elements do we choose? We choose n to the 3/4. Okay, and then we sort that set R. Of course, since it's n to the 3/4, we should be able to do that sorting in little o of n time. And then we identify elements D and U in the following manner. Notice that since there are n to the 3/4 elements in R, n to the 3/4 elements divided by 2 will be the middle element if you were to sort R. Okay, so from that middle element, you walk square root of n steps to the left, you will get D. You walk square root of n steps to the right, you will get U. These are your D and U, and these are elements chosen from R, but they're actually originally elements from S. Okay. Now that we have identified the elements D and U, we have to confirm that these are actually good elements, because, well, D and U have to follow some rules. If you recall, D and U have to be on either side of M in the sorted view of S, and the set C that we defined here, the set of elements in S that are between D and U, should be small. The cardinality of that set must be small. So we have to verify that we actually have a good pair D and U. How do we do that? Well, we compute the set C straight out of the definition, but this will require an O of n, a scan through the set of elements in X. And then we find the number of elements that are elements that are less than D, and the number of elements that are greater than U. Now we need to make sure that that a few conditions are satisfied. The number of elements less than D should not exceed n by 2. If that were the case, then the median is smaller than D, and so that's a bad choice of D. Similarly, the number of elements that are larger than U should also be less than n by 2. If it's greater than n by 2, then again your choice of U has been bad. And finally, the set C, its cardinality has to be small. In particular, we insist that it has to be no more than 4 times n to the 3/4. If it's more than that, then again our choice of U and D and U is bad. So we want to verify that our choice of D and U are good. If we realize that the choice of D and U are bad, we immediately output a fail. Okay. Now that we have ensured, now we're at step 8 here. We've ensured that it's not a failure. Our choice of D and U are good. So that at this point, we can easily output the median. And you should be able to figure out why this particular element in this sorted ordering of C is the correct median. So here's a couple of exercises for you. Suppose the algorithm does not output fail, meaning it's come up to line number 8 here. Okay. Then prove that the algorithm will in fact correctly output the median. So that simply requires you to ensure that this particular element that we are outputting is in fact the correct median. Okay, so that's the first exercise for you. Just ensure that you're convinced that this is correct, and also convince yourself that the running time of this algorithm is at most O of n. Okay, now that you've convinced yourselves of those two claims, now let's move on to the important aspect of bounding the probability of failure. Okay, because that's the only important key thing that's left. We want to ensure, I mean, as a consequence of exercise A, if it does not output fail, you're correct. So you just have to make sure that the probability of failure is very low. So let's look at it a bit more carefully. Feel free to pause and stare at this figure to convince yourself that the claims you're making are correct. A snippet of the pseudocode is available here for you as ready reference. So here's what happens. So we have the set S, and we have shown the set S in its sorted view. Of course, this is only for analysis purpose. And the median M is the middle element over there. And we are sampling R, a multiset R, which is this one over here. This is the multiset R, and we're actually sorting R. So once we sort R, it's going to be appearing as R1, R2, and so on up to Rn to the 3/4. Why? Because the set R has cardinality n to the 3/4. Okay, this set R itself has a median, and that is this element over here. Okay, and from that median element, we walk square root of n steps to the left and look at the element over there. That is our designated D. From the median element, we walk square root of n steps to the right, and that will be our designated U. Okay. And ideally, we want D to fall. If you look at D, not in the set R, but in the sorted view of the input array S, D should be to the left of M, and U should be to the right of M. That's the ideal requirement. And moreover, you also want the number of items here to be small. Okay, so these are the ideal requirements that we have. Now, since our main focus is to bound the probability of failure, let's try to understand why this algorithm might fail. What are some events that will lead to the failure of this algorithm? There are three events that will lead to failure. The first two are really symmetric, so symmetrically equivalent of each other. So let's look at the first manner in which the algorithm can fail. The element D that we choose according to the algorithm turns out to be larger than M, meaning in the sorted view of S, D appears to the right of M. Then that would be a bad event, because now what we wanted was D to be to the left of M, U to be to the right of M. Similarly, the second event is just capturing the mirror image, where the bad event here is that U is appearing is less than M, which means it's appearing to the left of M in the sorted view of S. So both of those are bad. And of course, the third bad event is this the set C, the elements in S between D and U has cardinality that is more than 4n to the 3/4. So these are the three bad events under which the algorithm is going to output fail. And we want to ensure that these three bad events occur individually with very low probability, and then we simply apply the union bound to say that even collectively they have low probability. So in the interest of keeping this lecture short, the third event, the, th the the task of bounding the probability of the third bad event, the cardinality of C greater than 4n to the 3/4, is left as an exercise. And as I pointed out earlier, events 1 and 2 are symmetric equivalents of each other, so we're only going to focus on the first bad event. And we want to show that the first bad event, namely that D greater than M, happens with very low probability. So let's look at that event a bit more carefully. So when in this, so recall that we have the sorted view of S over here, and this is the sampled set R, and we take the median in the set R, walk square root of n steps to the left, we find the D, and unfortunately D happens to be larger than M. So this is the way in which this bad event occurs. So how can this, what does this mean? This means that more than n to the 3/4 divided by 2 plus square root of n elements in R are larger than M. What do we mean by that? Well, all of these events, all of these items are all larger than M. Okay, and what's the cardinality of this set? That's this. This is, remember, this is the median element, and we walked square root of n steps to the left, so that we have to add that as well. Okay, and so obviously this looks like an unlikely event, but now we have to formally prove that it's indeed unlikely. So let's set up some notation to do that. So what we're going to do is define a Bernoulli random variable xi. It'll be a 1 if the ith random sample, the set R is obtained by sampling from the set S. So the ith xi equal to 1 if the ith random sample is greater than M. Well, remember that's the bad event, where when you have lots of items, in particular more than this many items larger than M, that's the bad event. So with that in mind, we're setting up the xi's in this manner. Okay, so now that you have defined xi to be 1 if the ith random sample is greater than n, otherwise xi is equal to 0. Okay, so this is our Bernoulli random variable, and it's the expectation of xi is close to a half. It's very, very close to a half. So we're just going to assume that it's a half. Okay, and of course now with these we aggregate these indicator random variables to define the set X to be the sum of all these indicator random variables, and there's a total of n to the 3/4 such indicator random variables, because R has cardinality n to the 3/4. So the expectation on X is that it will be n to the 3/4 divided by 2. So that's this. Notice that X is a binomial random variable, and so its variance is actually given by the number of Bernoulli random variables times the probability of the success of each Bernoulli random variable times the probability of failure of each Bernoulli random variable. So the variance of x turns out to be n raised to the 3/4 divided by 4. Okay. So now let's remind ourselves what the bad event is that we're trying to show is unlikely. We're trying to show that the bad event of more than n to the 3/4 divided by 2 plus square root of n elements in R are greater than m is small. So that's this probability that we have over here. And that probability can be phrased using the notation that we have built. So that probability is equal to the probability that the random variable x is greater than n to the 3/4 by 2 plus square root of n. Okay, and let's do a little rearrangement. We bring this term over to this side, and with an interest in applying Chebyshevs inequality, we take the absolute value. So we are actually slightly overcounting here. The probability that the absolute value of the difference between x and n to the 3/4 divided by 2 is greater than square root of n. This event has greater probability than the probability of the event that we are actually interested in. So that's good. We want an upper bound on the probability of the bad event. And now it's in a form that with which we can apply Chebyshevs inequality. And this probability is at most the variance of the random variable x divided by the square of the right hand side over here, which is and this term, since it's square root of n, this essentially is just divided by n. Okay, and so this whole probability turns out to be n to the minus 1 by 4 divided by 4. Okay, so by symmetry, the probability that u is less than m is also at most n to the minus 1 by 4 divided by 4. Okay, as an exercise, you will have to work out that the probability that the cardinality of the set C is greater than 4n to the 3/4 is also small, and in particular it's no more than n to the minus 1 by 4 divided by 2. Now these are all the probabilities of the 3 bad events, and when you add those 3 probabilities, essentially applying the union bound, you can infer that the probability that the algorithm will output a fail is at most n to the minus 1 by 4. So with that, we can conclude with our theorem, which states that the randomized algorithm that we have studied for finding the median of a set of n integers correctly outputs the median with probability 1 minus n to the minus 1 by 4 and runs in O of n time. So with that, we conclude the study of our median algorithm.